After exploring the translation problem that often confuses climate conversations, disentangling weather from climate, understanding how we measure a planetary fever, and distinguishing forecasts from projections, we now turn to the word that haunts every one of those conversations: uncertainty.
So let's communicate about the climate. Let's climunicate.
Hello, I'm Alberto Troccoli, and this is Let's Climunicate, a podcast where we talk about climate, weather, and society without the noise and without pretending any of this is simple. This is episode 5 of our 10-part solo series. So, as always, take off your coat, make yourself comfortable, and if you've been with us from the start, you know the rhythm. If you're jumping in here, welcome. We do curiosity here. We have a lot to uncover, so let's climunicate. Think about the last time you heard a climate scientist use the word uncertain. Maybe it was in a headline. Scientists uncertain about exact timing of ice sheet collapse. Maybe it was in a debate, someone quoting a wide range of climate sensitivity, or a model spread that covers everything from moderate warming to severe. And think about what you felt. Probably not curiosity, probably suspicion. If they're uncertain, how can they be sure? If there is a range, doesn't that mean they are guessing? Here is the misunderstanding about uncertainty. In everyday language, uncertain means I don't know. In science, uncertain means I know exactly how much I know, and here are the boundaries. One is ignorance, the other is measurement. And confusing the two has been one of the most effective ways of creating doubt about climate science. In fact, fossil fuel interests have deliberately exploited this confusion for decades, turning scientific uncertainty into a reason for public inaction. So before we go any further, let's define two words that scientists use very differently from the rest of us. Confidence describes how strongly the evidence supports a conclusion. Uncertainty describes the range within which reality is likely to lie. In other words, confidence tells us how sure we are about the direction. Uncertainty tells us how precisely we know that number. You can be highly confident that the bridge will carry traffic safely while still being uncertain whether its lifetime will be 95 years or 105. Climate science works exactly the same way. Imagine you're in a doctor's office. The diagnosis is in. The doctor says, I am 95% confident that this treatment will work. There is a 5% chance it won't. And here are the specific risks. The alternative is to do nothing, which has a much higher chance of harm. You don't stand up and say, you admitted uncertainty, you're just guessing. You hear the 95%, you hear the confidence, you make the rational choice. Now, imagine a climate scientist says, we are 95% confident that human activities are responsible for most of the warming observed since the mid-20th century. Too often, the public hears the 5% doubt, the range, the likely, and thinks they don't really know. It's still debated. But it's the same statement, the same structure, the same honest quantification of confidence. The difference is not in the science, it's in the translation. We are trained to trust medical uncertainty because we want to live. We are trained to distrust climate uncertainty because it feels uncomfortable when it challenges existing habits, investments, or worldviews. And so the word uncertain becomes a weapon instead of a descriptor. Uncertainty is not the absence of knowledge. It is the geometry of knowledge. It is the shape of what we know, outlined honestly against what we don't. The design problem is that modern public discourse often treats uncertainty as weakness. A headline that says, scientists uncertain, gets more clicks than one that says, scientists quantify confidence. A politician who says, the models are uncertain, expects you to hear the models are useless, even though the models are explicitly designed to explore uncertainty ranges. In fact, uncertainty sits at the very heart of modern science. Every measurement in physics comes with an uncertainty estimate. Even the most precise instrument in the world cannot measure anything with perfect accuracy. Uncertainty is not a flaw in science. It is how science quantifies its own limitations. In episode 1, I told you confusion is a design problem, not an intelligence problem. This is where the problem does its most damage. We have built a public conversation where admitting the width of your error bar is seen as losing the argument, rather than as the mark of intellectual honesty. But climate science is not guesswork. It's a weighted probability. It's a risk assessment. It's among the most rigorous attempts anywhere in public policy to quantify uncertainty. And today, we're going to learn how to read it. So how do we read uncertainty without becoming either overconfident or unnecessarily skeptical? Here are our 3 translation rules. Rule 1, uncertainty is a range, not a void. Remember rule 1 from episode 1? We think in anomalies, not absolutes. Here, we think in ranges, not binaries. When the IPCC says that doubling atmospheric CO2 is likely to warm the planet by somewhere between 2.5 and 4 degrees Celsius, they are not saying we have no idea. They are saying we have ruled out the lower end and the higher end through multiple lines of evidence. And here is the remaining window. The range is the shape of the knowledge, not its absence. Think of it like an archery target. The arrows do not all hit the bullseye, but they all hit the target. The fact that they don't all hit the exact same spot doesn't mean the archer lacks skill. It means that the archer understands the limits of precision. The error bar is not a confession of ignorance. It is a quantitative description of the limits of measurement and current knowledge. And in climate science, the precision is remarkable. We can estimate the global temperature anomaly to within a few hundredths of a degree. We can detect the human fingerprint in the warming pattern. The uncertainty exists at the margins. How much cloud feedback will amplify warming? How quickly will West Antarctica respond? But they do not touch the core. Rule 2. Independent evidence builds confidence. In episode 2, we separated trend from weather, the signal from the noise. Here, we separate the trajectory of knowledge from the illusion of doubt. A single uncertainty measurement, a single model with a wide spread, a single paleoclimate proxy with ambiguous resolution. None of these cancels the consensus. They are inputs into a larger calculation. And when multiple independent methods converge, uncertainty shrinks. We discussed this in episode 3. Thermometers, satellites, weather balloons, ocean buoys, ice cores, tree rings, they don't share the same biases. They don't share the same instruments. Yet, they converge on the same trend. Warming since the Industrial Revolution, accelerating in recent decades. The probability that they are all wrong in the same direction by the same amount for the same reason is vanishingly small. This is why the IPCC can say virtually certain that human activities caused most of the warming observed since the mid-20th century. This is not rhetoric. It is a statistical statement backed by compounding of independent evidence. The uncertainty of any single study becomes much less important when viewed alongside a broader body of evidence. Rule 3. Not all uncertainties are equally important. In episode 2, we talked about scale, how your local weather is not the global climate. Here we apply scale to confidence itself. We are highly confident that CO2 absorbs and re-emits infrared radiation, trapping heat in the atmosphere. This is laboratory physics, measured since the pioneering experiments of John Tyndall in the middle of the 19th century. We are highly certain that atmospheric CO2 has risen from 280 parts per million to over 420 parts per million since industrialization. We are highly certain that the planet has warmed by around 1.5 degrees Celsius relative to the pre-industrial baseline. The uncertainty lives at the edges. Will the Amazon flip to savanna, and on what timeline? Will the Atlantic meridional overturning circulation slow by 20% or 50% by 2100? Will your city get wetter or drier in 2050? These are real uncertainties, but they are regional, temporal, and mechanistic. They do not cast doubt on the core physics any more than not knowing tomorrow's lottery numbers cast doubt on arithmetic. The design problem is that both the media and some commentators often zoom in on areas of uncertainty. But what about clouds, and present them as if they undermine what we know with much greater confidence? It doesn't. Scale matters in confidence space too. Let me give you an example that brings this together, using the data we've already discussed. If you're watching on YouTube or Spotify, take a look at this graph. What you're seeing are several independent global temperature datasets from organizations like NASA, NOAA, Copernicus, Berkeley Earth, and Archery. The lines don't perfectly overlap, nor should we expect them to. Some years appear a little warmer in one dataset than another. That's uncertainty. But now, notice something more important. Every one of those lines tells the same story. The planet is warming. The exact decimal places differ, but the trend, it does not. And that's confidence. If you wanted to weaponize doubt, you'd point to that disagreement and say, see, they can't even agree on which year was hotter. The fact is that the noise is in the hundreds. The signal is in the cluster. This is exactly what we mean when we say uncertainty is not ignorance. The scientists know exactly where their methods disagree. They publish those disagreements. They are not hiding uncertainty. They are displaying it because the public deserves to see the error bars. And the error bars, in this case, are so small relative to the trend that they confirm the story. The same is true for the model ensembles we discussed in episode 4. When you see a spread of projections from 1.5 degrees to 4.5 degrees by 2100, the spread is not a confession of ignorance. It's a map of human choice. The lower end requires rapid decarbonization. The higher end reflects continued fossil fuel dependence. The physics is largely known. The human pathway is the variable. If this is helping you see uncertainty as rigor rather than weakness, give the episode a like. Share your thoughts in the comments and send it to someone who says the science is uncertain, as if that ends the conversation. It generally helps the podcast reach people who need a clearer, calmer explanation. In the coming episodes, we'll continue unpacking this step by step. We'll explore why hitting climate targets doesn't always mean we're safe, and how to think about climate risk without being paralyzed by it. So subscribe if you haven't already. Turn on your notifications so you don't miss any of our episodes. If you've ever used the word uncertain to dismiss a climate finding, or if you've watched someone else do it and felt the conversation grind to a halt, you're not alone. We have been taught to see uncertainty as the end of a conversation rather than the beginning of a better question. Science does not eliminate uncertainty. It measures it. And uncertainty is where the science lives. It is the honest boundary of our knowledge, not its absence. The greenhouse effect is established. The warming trend is measured. Human influence is supported by overwhelming evidence. What remains uncertain are the exact magnitudes, timings, and regional consequences, because every measurement and every projection comes with a range, as well as our willingness to act on what we already know. But before we can act, we need to understand. And to understand, we need to communicate. See you in the next episode.